Hello everyone. This is not an SMO Open Crash Course because, to be honest, it's pretty impossible to have a crash course for the SMO Open. The SMO Open is probably going to be the last Math Olympiad that many of you will take. It is possible that maybe you would be taking the AMC and some other smaller competitions, but for Singaporeans, the SMO Open is probably the last one. Which means that everything you have ever learned for Math Olympiads is potentially useful. And claiming that I can come out with an hour or 2-hour video to talk about everything we've learned in Math Olympiads is frankly very ridiculous. But the first thing that you need to realize is precisely that the SMO Open is testing you on everything you have ever seen for Olympiads. That's important to know because when you're solving the SMO Open problems, don't think of it as SMO Open problems. It is usually possible to qualify for the second round and even just to get a silver just by solving questions that are quote-unquote SMO junior level or SMO senior level. And this is the most important thing I can possibly say today. If your goal is to get a decent award, for every question, pretend that it is a SMO junior problem and ask yourself how you would do it. Chances are there will be about 6 or 7 questions that you can solve just by using no harder than the SMO junior method. Let's say we look at this problem here. The rectangle has area 180 and there are 2 triangles with area 60. That means that half the rectangle has an area of 90, and so ABE is 60, AEC is 30, AFC is 30, ADF is 60. So these sides are split in a 2:1 ratio. That's SMO junior stuff. This means that your triangle ECF is going to be 1/3 the height and 1/3 the width of half the rectangle. So the area is 10. And that's it. Answer of your shaded area is 50. Now you might be thinking, oh no, this is obviously cherry-picked. And you're correct. It is cherry-picked. Not every question is going to be like it's from the SMO Junior. More of them are going to be like it's from the SMO Senior. Some of you are also taking the SMO Senior while doing the SMO Open. Some of you have just taken the SMO Senior and are now taking the SMO Open for the first time. Treat the SMO Open questions as if they are just SMO Senior questions as well, except that usually they will be asked in a more interesting looking way. So for instance, if we look at this problem over here, it just tells you that you have a parabola, y equals to half x squared, and then a circle inside it and another circle inside it, and you're asked to find the sum of the radii of C1 and C2. So all you need to do is to find the equations of C1 and C2, and basically that means finding the centers of C1 and C2. So we can start with saying that C1 has a center by symmetry 0, r, and the radius is r. So x squared plus y minus r squared equals to r squared. Let me simplify a little bit. And now we want to basically ensure that for my choice of r, this is only going to intersect with y equals to half x squared once. How do I do that? Well, a very simple way that I can make sure that it is going to intersect only once is to just substitute in y equals to 1/2 x squared. And maybe it is easier to let x squared be 2y and put it into here. So you want to make sure that this only has one solution. We can use the discriminant, but in this case you realize that the y squared minus 2ry plus 2y already has the solution y equals to 0. So the only way that that would be the only solution is that this simply becomes y squared equals to 0. So we need r to be equal to 1 so that the back part cancels out. And so straight away, you get the first radius, and then you repeat the same process again. Right? This is going to be 0, 2, and then now I will call this 0, 2 plus k, let's say, where k is your new radius, and then repeat with the intention of doing the same thing one more time. You want to make sure, once again, that y equals to 1/2 x squared is going to touch this and give you exactly one solution for y. That would give you two values of x, but one solution for y. So likewise, you can substitute in x squared equals to 2y. And you want to make sure that the discriminant is equal to 0, which I will leave the details to you. But you can tell there is nothing specific to the SMO Open about this. It looks scary. It mentions parabolas. It has touching circles. No calculus involved here. Nothing fancy at all. Pretend that the questions are from the SMO Senior, and that would add on another 6 or 7 questions. So if you just solve questions that are at the SMO Junior and Senior level, you can easily get half the problems and get into the second round. That's the most important thing I have to say, but there will obviously be a challenge in identifying which of these questions are easy. And 2.5 hours is pretty limited. Sometimes we will miss out on an easy question just because we don't have time to try every of the 25 problems. And so I can't stop here. I'm just going to mention a few simple ideas which can realistically be conveyed inside a 1 over hour video. The easiest one is on summations. Summations is a topic that is in A-level syllabus under sequences and series, and you also have a method of difference. However, you're not going to be told what method to use. So it's important to just precisely know what are the options. Now, the first option is that it's going to be a formula, like let's say your arithmetic progression or geometric progression, where you have some formulas. That's the easiest and most likely way to handle problems when it tells you something that looks familiar. This is not one of those. So we go to the second method. The second method is to do grouping or pairing. Now that's very tempting here because of the fact that it is set up in a symmetric way from negative 2021 to positive 2021. So it looks like there is some sort of symmetry around k equals to 0. And we can just check what happens if I were to combine the positive and negative terms. It takes only one step, surprisingly enough. Right, this was a question 1 from 2 years ago, so it's not supposed to be extraordinarily difficult, but it's a good learning example for how to approach summations. Each pair adds up to 1, and so you have got 2021 pairs And don't forget that k equals to 0. K equals to 0 gives you a half. Okay, so your answer is 4043. Floor of 2s has a redundant floor over here. It's just essentially 2s is 4043. So that's one way that we can handle these summations. The other is going to be your method of difference. Now your method of differences, which is to say telescoping sums, effectively is trying to make everything cancel out. I do like the name method of differences though, because you are essentially trying to make the summoned into a difference of two consecutive terms. Essentially, you want it to look like f1 minus f2, f2 minus f3, f3 minus f4 for a suitable choice of function f, so that when you start adding them, things will all cancel out. And so you're trying to make it into a difference. If you're trying to make it into a difference, there must be a difference, right? What I will do here is to write this as k plus 1 minus 1. This will allow you to cancel k plus 1, and immediately you will get 1 over k factorial minus 1 over k plus 1 factorial. For those of you who are doing A-levels pretty soon, normally this would be given as an initial step. This would be given as a part A, then part B will be hence find Sn, or maybe hence find S100 or something like that. You usually don't get that benefit for the SMO. So one simple way would be to just try to look for a pattern. However, it's useful to just ask yourself, where can I meaningfully insert a negative sign? And this will be where you can insert it. I would sometimes consider this to be also a SMO senior style question, because the SMO senior also does have summations. Another thing which is sort of a SMO senior style question as well would be things that involve the Cauchy-Schwarz inequality, except that the Cauchy-Schwarz inequality is part of a H3 math syllabus, so there will be a number of you who have now learned it as school syllabus and not just as an Olympiad specific technique. The Cauchy-Schwarz inequality, if you're watching this as an SMO Open video, is most easily understood using the vector dot product. For instance, if I were to use just ABC and XYZ as my two vectors, and I take dot product, I know that it's going to be the two magnitudes times cosine of the angle between them. So I can say that the absolute values of this dot product is going to be less than or equal to the product of the magnitudes. If you were to open this up, you get Cauchy-Schwarz. So you get Cauchy-Schwarz essentially as being a dot product is less than or equal to the product of magnitudes. And this is really helpful if you are trying to apply Cauchy-Schwarz and you always found that you had a little bit of trouble. You should look at an expression and do two things. First of all, ask yourself whether it looks more like a dot product or like a magnitude. Second of all, you should ask yourself which direction does it belong on. And that depends on the question. If it says minimum, it means that you would like to say that this expression is greater than or equal to something. If I tell you that it's greater than or equal to 10, that suggests the minimum is 10. If I tell you it's less than or equal to 10, it doesn't tell me anything about the minimum value. So if you know that it's greater than or equal to, it means that it belongs on the magnitude side, which makes sense. And so what you can do is to ask yourself, what magnitude does this look like? Well, there are 4 variables, so we can just make a 4-dimensional vector with these 4 things inside. And the other vector, well, there's nothing else here, so I'm just going to pad it with 1, 1, 1, 1. So you're going to get square root of the expression you want. I'm going to call this A. So it's going to be less than or equal to what you want. And the magnitude of the vector 1, 1, 1, 1 is just 2. Sorry, that should be 4 first because I have the whole square root over there. So this side here, if we write the dot product, it's just going to be x plus y plus z plus w plus 5 plus 10 plus 20 plus 40. So we get just 80. And straight away, A is going to be at least 1600. The Cauchy-Schwarz inequality is also equivalent to the QM-AM inequality if we use it like this. But I think now that you have some familiarity with vectors, this is an easier way to express it. Let me show you another example of how we can use Cauchy-Schwarz. It's not in the way that you might think. Remember that Cauchy-Schwarz, AMGM, or any of your inequalities are meant to provide information. They are not meant to confirm a property. If you used AMGM, let's say, to say that 1 plus 4 divided by 2 is greater than or equals to the square root of 1 times 4. Well, I knew that 2.5 is more than 2. That's not news to me. So this is utterly useless. So don't use Cauchy-Schwarz and say that, oh, x1 squared plus x2 squared plus x99 squared, and then compare it to something to do with x1 plus x2 to x99. I don't even want to write this properly because that doesn't tell me anything. 960498 versus 9702. I'm not interested in this either. Because the question is asking you for the largest possible value of x1. So what you should do is to ask yourself, why can't x1 be anything I like? And the answer is that if your x1 is going to be poorly chosen, then the rest of the values are not going to be real numbers anymore. It cannot be satisfied. So the rest of the values should be your focus. The rest of your values, meaning x2 to x99, can be compared. And I'm going to use the same vector approach to write it. This dot product is less than or equal to the magnitudes of these two vectors multiplied together. So x2 to x99 is less than or equal to the square root of the sum of squares from x2 to x99, and then just 98. So I'm going to leave you to do the substitution and to solve for x1. One thing you might notice, if let's say that you just paused the video a few seconds ago and worked out the rest of it, you're going to pause it for quite a while, right? Because these are very unpleasant numbers. So just a tip, right? For the SMO Open, sometimes you're going to get very big numbers. And you should also look for numerical optimizations as far as possible. What I mean by that is try to look for things that will make your life a little bit easier for calculation purposes. So for instance here, 9702, if you factorized it, is 98 times 99. And you can guess that this is actually related to the first one. It is 98 times 99 times 99. So that may help you when you're substituting into here and are trying to simplify a little bit and solve for x1. So look for calculation stuff that are more optimized as well, so that you don't have to just waste all your time on calculations. The SMO is not about calculations, but in an era where we are used to using our graphing calculator for everything, it's a little bit tempting to just not focus on the calculations. But finding a fast way to calculate is also part of the challenge. Now, speaking of graphing calculators, Riemann sums is one of the things that is not normally introduced to us until a first year undergraduate calculus course. But the concept is very simple. It's just going to be from a graph. Assuming you know what the Riemann integral, a normal integral, is, calculating it is not going to be much of a problem. Now, the concept of a Riemann sum is effectively that in order to find the area, let's say, underneath a graph, if I want to get this shaded area, I can split it into a bunch of rectangles and add up the areas of those rectangles. And if my rectangles are close enough to covering everything, that would be a good estimate, which would happen when I have more and more rectangles. That's what n goes to infinity represents. Right now, as you are looking at this computer screen, you do realize that curve that I just drew is a bunch of rectangles, isn't it? This is, after all, made of pixels. Whether you're watching on a phone, a tablet, a laptop, or a smart TV, it's pixels. So you are actually already looking at a bunch of rectangles anyway. Just that we are talking about infinitely many. And so the way that you would approximate this is going to be just the width. Let's say the width is 1 over n if you have n rectangles. And you're just going to take f of 0 plus f of 1 over n all the way to f of n minus 1 over n. That's if you are taking the area from 0 to 1. If you're taking the area from 0 to 2, then change 1 over n to 2 over n. If you're taking the area from 0 to 3, change it to 3 over n, and so on. So what you want to do when you're given something like this is to realize that you don't actually have a nice way to sum this up. And so the limit going to infinity usually represents something like this. This is not like the summation we did earlier. You want to rewrite it in such a way. So I'm going to do the weird looking task of the weird looking step of factorizing out 1 over n. Now that takes out n squared, so you have got 1 plus k over n. Now you realize actually that this becomes your function f of x 1 over square root 1 plus x is the function. And you are basically substituting in all the values from 1 over n all the way to n over n. Now I know this is a little different from what I wrote on top. It's going to infinity, so changing one of them from 0 to 1 makes no difference. And so it becomes an area which is now just testing your integration skills on a relatively simple integral. If you know how to do the integral, I'm going to leave this to you. If you don't know how to do integration, unfortunately, this is not going to mean very much. So your best bet is going to be just trying some small cases if you do not have a knowledge of integration. Remember that if you can get a rough estimate, it's usually good enough. So a similar thing happens here in this other example, which I'm going to leave to you, except to just write it down in a very familiar looking way again. Yeah, that's all that it is. Generally, the SMO Open is going to ask one question on calculus, one question on vectors, one question on complex numbers. Essentially, all the so-called JC-specific topics are going to be asked about once. So if you're not a JC student, or you're a JC student that hasn't yet learned that topic, don't feel bad to just forego one or two of these questions. Remember what I said, the SMO Junior and SMO Senior ideas can solve enough questions to get you into the second round and will probably take up 2.5 hours of your time already. But this is useful for those of you who have already learned calculus because it's a very short solution if your foundations in calculus are secure. I want to talk about something else, which is an easy mark occasionally, which is functional equations. Now, functional equations is a really broad topic, and for the SMO round 2, it can be really hard. For the SMO round 1 though, you can guess the function half the time. So if you were to look at this over here, I think you would guess straight away that that looks like a squared minus b squared is a minus b, a plus b, right? So if you see a functional equation, start by guessing the function. That's wrong, isn't it? Because f of 1 is 1 over 101. Never mind. Just adjust it by a constant, because you see that f appears once in every term on the left and right. So therefore, if you just scale f up and down by a constant, it will still give you equality. Now this is not just a good idea for round 1, this is also a good idea for round 2, except that for round 2, it gives you 1 out of 10 marks. In round 1, it can give you 1 out of 1 mark. So we can be very happy with the guess. As to how we're going to justify it, it's going to be a little bit difficult to summarize that in a few minutes, but one of the common ways is just to make use of what a functional equation is. For any x, y, which are real numbers, is what makes a functional equation a functional equation. You can put in anything you like. Anything. That's important. You can put in anything you like. So make use of that. For instance, if you're given this equation here, it's quite hard to guess the function. So don't worry about guessing the function. Instead, what you can do is just to realize that you're given f of 1 and you want f of 10. There are two functions here, f of x plus y and f of x minus y. There are two instances of the function f, I should say. So just substitute xy such that x plus y equals to 10 and x minus y equals to 1. Of course, that would be 11 over 2 and 9 over 2. And then after a little bit of calculation, you're going to get f10 straight away. Now this is making use of the fact that for the SMO, they are not really able to ask you for the entire function. It can only ask you for the function at a particular value, right? Now having said that, it is possible that for a function, it may not be possible to determine it everywhere, and that's why they're asking you for one particular value. So sometimes you really cannot solve the function. So this may not just be around one shortcut. There are instances where you can only find the function at a few locations and nowhere else. Continuing on our discussion of functions, you don't need to find what the function is, but when they tell you about a function, there are some properties of a function which you would like to consider. For one thing, the initial thing that you should understand about a function is that a function has two things involved. It has a rule and it has a domain. Now, the domain is something which, if again, as A-level students, you may have had a lot of annoyances with seemingly trivial questions that are wasting your time on very boring stuff. Right? This is a function that is now restricted from 1 to 10. This is a function that is from 1 to infinity. Aren't they the same thing? Well, to an extent, you might think that a function is just a rule. But that's not always the same thing. For example, all vending machines follow the same rule. You put in money and you get the item you paid for, a drink or a snack. But the domain would be what snacks are there? What snacks can you select? Or what drinks can you select? I'm sure you would agree that a sandwich machine is not the same as a drinks machine, is not the same as a coffee machine. So vending machines are not the same. Now here, one of the things that you'll see is that there are a few interesting functions over here. Now, square root 4 minus x squared and square root x squared minus 4 are kind of in opposition to one another. Because this requires x squared is at most 4 and this requires x squared is at least 4, which is not exactly the same thing. In fact, it's exactly not the same thing. How do you get that to happen? I know. X equals to 2. Wait, no. X is not equals to 2. So, how do I make this into even a real number? X is minus 2. It's going to be the only value in the domain. Or rather, it's the only value where S is real. So don't forget the domain. And also, don't forget about your other function properties. For instance, here we have a couple of equations which we can't solve. If you want to challenge yourself, you can try to just check if you are able to even estimate the value of x. It's not that easy. But you should ask the question, even for the one we just saw, how am I even supposed to find S when S could seemingly be anything? Here, you should be asking the question, how is it that x1 plus x2 is nice when x1 and x2 themselves are clearly going to be very ugly? So, usually, math is like this. Effort needs to be made in order for an answer to be nice. If you were to just throw in random values, things are not going to be nice. So when you need effort, what you need to ask is, what effort was put in? What's special about this? And the answer is that, well, log 2x and 2 to the power of x are inverses. Of course, 20 minus x is just repeated, so let's try to draw a graph. You do not have a graphing calculator, but remember, function properties. When we talk about drawing a graph, right, you know that there are two different verbs that can be used. Plot a graph and sketch a graph. Plot a graph is what you are going to be doing in your physics practical, right? You do an experiment and then you will note down all the data points, and the data points are going to literally guide your graph. It's usually on a graph paper if you are doing it in a formal setting. Sketch a graph just means you want a few key features. And so, for example, if I had the graph of y equals to x squared plus 1 and x squared plus 2, all I want is to make sure that one of them is on top of the other and shifted up. I don't care about where is 1. I don't know. It does not matter. So, likewise here, 2 to the power of x, I just draw it like this. Now, I want to draw the line of y equals to x because y equals to log base 2 of x is going to be the reflection of this over y equals to x. They are inverse functions. So that's the feature that I want. Now, is this to scale? I don't care. I don't even know what is my scale. But then 2020 minus x, where is it? I don't care. But it is going to have gradient minus 1, meaning it's going to be perpendicular to my dotted line. And therefore, it's going to be symmetric when you look at the two intersection points. x1 and x2, if I take this, it tells me that x1 plus x2 over 2, which is going to be the average, is the intersection between y equals to x and y equals to 2020 minus x. Which obviously, the intersection is just 10, 10, 10, 10. And so x1 plus x2 is 2020. This is true of all Olympiad questions. They know you don't have a calculator or a graphing calculator. The competition is set up like that. Which means that you always have to keep asking the question, what's special about this? Because if you just replace this by two generic equations, or even you just replace log 2x by log 3x, we can't solve it. So ask yourself, why can I solve this? What possible chance do I have to solve this? It has to be chosen very specifically. I want to look back to the theme that we started this video with now. Right? We started by saying that treat it as a SMO junior problem, and then you are probably saying that I don't really see that many questions that are like the SMO junior. Well, I didn't say round 1, did I? Some of them are like junior round 2 questions. But the difference is that you do not need full solutions. Now, if you ask me to, let's say, take a SMO in 2.5 hours with 25 junior round 2 questions, I have no hope at doing it, and I'm sure no one in Singapore would be able to write 25 full solutions in 2.5 hours. So, without full solutions, that's what we're trying to say. For a round 2 problem, there are 2 elements to it, right? For a round 2 problem, usually it has a construction and a proof. What I mean by that is, for instance, if you told me that the best outcome is 10, the solution would involve 2 things. First, tell me how did you get 10? Secondly, tell me why you can't get better than 10. Now, if that is what you're telling me, then I know the answer is 10 for sure. In the open round 1, however, you don't need to show both, which means that you can look for either the construction or the proof. And usually that is enough, and you don't need to write any of it down. So take for instance this question, right? This question tells you that there is a giant table with ones and minus ones, and the product of numbers in the first row and the first column add up to 0, second column and second row add up to 0, and so on. In other words, that your products all are going to look like a 1 and a minus 1. So you have got two different ways that you can focus on this question: the construction or the proof. Now I'm going to sort of talk about both of these. And the key thing is that you really only need to do one of them in a round 1 setting. First of all, let's say you're trying to do the construction. Obviously, you don't start from a 20 by 20 20 by 20 table. You can't even draw that, right? So you start with something smaller, like let's say a 4 by 4 table. So you want to put in some ones and minus ones so that the first row and first column there's a 1 and minus 1, second row and second column there's a 1 and minus 1, and so on. First thing that we realize is that you don't really need to write in ones, right? Ones are just going to be doing nothing. It's about the minus ones. So I just need to write in the minus ones. So if let's say that you are trying to make it work, one way that you could do it is to say that, okay, I'm going to try to make all of these minus ones and all of these ones. So maybe one way to do that is going to be something like this. But is that necessarily the best way? So you can experiment for a few minutes. Just look around, and at some point you may come to the realization that, okay, I technically don't need to put all the ones as the column products and all the minus ones as row products. I can have a mix. So for instance, if let's say I just put a minus 1 here, and then I put a minus 1 down here, that's actually enough. So if you just landed on this or something similar to this, you realize that that's actually quite a good idea, isn't it? If you have got a bigger grid, just use half of the so-called negative diagonal and put minus ones on there. And this would give you an answer which is, well, half. Now I put a question mark there because admittedly, we don't know that this is correct, but we are about 60% sure that that's quite good. Now let me give you the proof. The proof is actually very simple, right? Just imagine you start with an empty grid. I'll just draw a 4 by 4 just to show you why is it that this is a reasonable argument. Now, at first, they are all ones. Each time when you put in a minus 1, it's going to flip 2 signs. Right? For example, if you put it here, then these are the signs that you flip. If you put it here, then these are the signs that you flip. So each minus 1 will flip 2 signs. Now you know that you need to flip 4 signs. And so therefore, you need to at least have 2. And of course, the logic will also apply in the general case, where instead of 2, it will be 2020. And instead of 4, it will be 4040. Sorry, no, that's still 2. Each minus 1 does still flip 2, but you need to flip 4040 signs, and so that confirms. You know what? I'm talking nonsense. You need to flip 2020 signs, and so the answer is 1010. I do apologize. So each minus 1 flips 2 signs. You're supposed to flip 2020 signs, and so there are 1010 minus 1s at least. Now this is a proof that says that it's at least 1010. How you actually manage to do that is on the left. So both of these are sort of like 70% certainty. But that's often enough in a competition setting. One more example of that. You see, we don't always have the ability to do both. That's the key thing. It's not about whether we can do it eventually, but there are time constraints. So here the question is asking you, how many numbers can you pick so that all the differences are the products of 2 distinct primes? Now, if you ask me to just select numbers, I don't even know where to begin, to be honest. But my idea is going to be something like this. I'm going to try to just do a bound, which is a proof. And I'm going to look for a reason why it isn't huge. In other words, why can't I have 100 numbers? Why can't I have 1000 numbers? Now, sometimes that's a very silly question, but it's your starting point. Ask yourself, why can't I have 1000 numbers? So, what would be wrong with 1000 numbers? You're looking for the simplest explanation possible. And so for me, I think the simplest explanation possible, if I have 1000 numbers, I will at least have 2 of them have the same last 2 digits. Right? So, I mean, I only need 101, but if I just have a huge number, say 1000, then 2 of them with the same last 2 digits, and so their difference is a multiple of 100. Obviously, if the difference is a multiple of 100, it's not a product of 2 distinct prime integers. So you have found just some pie in the sky reason why you can't have 1000 numbers, and then you try to improve it. So once you just find a very random reason why it can't be huge, shrink it back down again and ask yourself, well, I mean, it doesn't have to be last 2 digits, right? The difference is a multiple of 100 is a problem. If the difference is a multiple of 50, that's also a problem. If the difference is a multiple of 20, that's also a problem. So you can shrink it down. And the smallest number that causes you a problem is that if your difference cannot be a multiple of what? We can bring it down all the way to 4. The difference cannot be a multiple of 4. Which means that you at most have 4 numbers. If you have 5 numbers, 2 of them by pigeonhole will have the same residue modulo 4, and therefore the difference will be a multiple of 4. So this already gives you a very good bound. And I'll tell you that the answer is 4. And you can roughly just try to see how this is going to go. if you wanted the specific example that I have in mind, you could do something like this is 2 times 11, 3 times 11, and 2 times 11. This is one example that will work. But it's not the only one. But my point is that if you can't figure out an answer by just trying out values, look for a reason why it can't be huge first, or look for a reason why it can't be small first, depending on what's asked. And if you can't find an example, sometimes just the proof / explanation is enough to give you an answer again with a 70% certainty. That's the spirit of round 2, but you get to do a watered down version of it in a time limited open round 1. The SMO Open still has that relic of the SMO Senior as well, in that there's a lot of algebraic manipulation, except that it may be a little bit harder, or at least harder looking. If you look at this problem over here, A, B, C, D add up to 8, and this sum of fractions is 3 over 10, our go-to of let's try to guess doesn't really work. However, all is not lost. All is not lost, because there is a very simple way that we can transition from the given condition to what we are trying to find. Namely, what's AT? AT is a constant. And it said find the value. So, what you can do is to think, how is this going to become that? Well, I need to make the A's disappear. And how far away is A from disappearing? It needs B, C, and D to disappear and become a constant. So I can just top up the rest of it. So just top up the missing terms, and that comes at a cost of 1 per fraction. Just top it up, and you get 3 over 10 plus 4. Of course, this becomes just all 8. And so your answer is going to be 43. Now, by the way, humorously enough, there's actually a little bit of a problem here. Now, you may not notice this, but the problem is that this is actually impossible. And you can prove it, so I'll leave it as a challenge. Proved by Cauchy-Schwarz that this is impossible. It's a bit of an accident, really, but it's impossible. In fact, it's not that difficult to prove by anything that is impossible. So what the challenge is to find the actual minimum. right? If you just want to show that it's impossible, that's not that difficult, right? So why did I include a wrong question? This is an actual SMO Open question as are the rest. If you see a question that's wrong, just try to solve it properly first, but that doesn't change the fact it's wrong, and most likely the question is going to get voided. I believe this question was voided, and in the last 5 or 6 years, there have been at least 2 or 3 questions that are wrong, either in the sense that there is no correct answer, or in the sense that the question's conditions can never be satisfied. My suggestion? If you see something that's wrong, just ask and then move on, because you may not get an answer in the duration of a 2.5 hour contest. And to be honest, this does happen quite often, that the question setter has something in mind and didn't realize that what they wrote down is actually impossible. It's happened to me before as well, so it does happen. I've included another question which is not mistaken, thankfully. And this other question uses an algebraic identity. The identity that it uses, if you were to just rearrange this equation, is a pretty well-known identity. It's your a cubed plus b cubed plus c cubed minus 3abc identity. If you don't know it, now hopefully this is the first time you're seeing it, this is your factorization. And the important reason why you want to know some of these identities is that for the SMO Open, they're not going to most likely just give you a question that is so obviously a difference of squares or something that is so obviously simple. It will use slightly more complicated identities, but in terms of approach, it's the same. It just uses a more sophisticated result. Another example will be the Sophie-Germain identity, or Sophie-Germain, which is that you can factorize a to the 4 plus 4b to the 4 if you use a bit of a clever-ish completing the square approach. Don't need that for this question, but I just wanted to mention that sometimes if you're reading solutions in an SMO book, those are just identities. So in this case, if you want to find the graph with this equation, you want to know what is the shape of this graph, right? And the same question as earlier, how do we actually draw this graph? We don't know how cubic graphs work. Most of them are so-called elliptic curves. They are not even going to be very possible to do by hand. Elliptic curves are part of the solution to Fermat's last theorem. So if you want to actually use your identity here, it's not difficult. But the key thing is to look for an identity. So the key thing is to look for an identity. And then from there, once you have done the factorization, then things are going to be a lot more straightforward. Right? So this is going to be a line. And I'm going to leave you to figure out what's going on over there. As a hint, if you can't see what's going on over here, try to see what's going on in the original identity. You will be able to see something interesting about this expression and when it can be equal to 0. So as much as I said there are going to be a lot of questions that are like SMO Junior, SMO Senior, things are going to be spiced up a little bit. If let's say it's an identities question, the identities are a bit trickier. If at the start we saw something like our discriminant question, the discriminant question is going to be just a little bit more complicated than the SMO Senior's discriminant question. Alright, so one final theme after we move on from algebraic manipulation, the idea of binary representation. Now, binary representation is something that you don't need to know a lot about, but it's a useful picture to have of different number representations. Now, binary, which is base 2, means that your digits are 0 and 1, is what you see every time in computer science. And in case you didn't already know, the zeros and ones are not just something you see in the matrix. The zeros and ones do represent a number system. What I'm writing here are the numbers 1 to 10 in binary, and it's basically that your place values in binary are 1, 2, 4, and 8, and so on, your powers of 2. So for instance, if I wrote 10011 in binary, usually a subscript 2 means in binary, your place values instead of powers of 10 are powers of 2. So 1 down here is 2 to the 4, and then the other ones are 2 to the 1 and 2 to the 0. So it's 19 in our usual base 10. I hope you can see the echoes of binary in this question. All the possible non-empty finite subsets of 3 to the 0, 3 to the 1, 3 squared, 3 cubed, and so on are arranged as a monotone increasing sequence. Hopefully you can tell that this is kind of like binary, except that your place values are now powers of 3. Effectively, they are borrowing the idea of binary. So how does this work? To find A217, you're going to convert 217 in binary and then convert that into a value with powers of 3 as place values. So as an example, if I took the number 5, 5 is 4 plus 1, 4 is 2 squared, and so this is 101 in binary. And then 101 gets converted back into 3 squared plus 3 to the 0. Another way of thinking about it is that 2 squared plus 2 to the 0 becomes 3 squared plus 3 to the 0. So you do the same with 217. And you just write down your powers of 2. The conversion for binary is very simple. Just keep on taking the biggest power of 2 that you can. So 128 is the closest, then 64 can still fit. You're left with 25. So 16 plus 8 plus 1 is going to be your conversion. And then A217 just switches all of these to powers of 3. So a very simple idea. But it's useful to have this picture of binary because it also gives you some intuition for various things about the sum of powers of 2. For instance, because you see that 111 comes before 1,000. Later on, 1111 comes before 10,000. And so that corresponds to a geometric series. When you add up all the powers of 2, it's 1 less than the next power of 2. So some properties like this can be discovered more easily or can be noticed more quickly if you have this idea of binary in mind. And one more question with this idea here, that is somewhat binary-like, can be seen in this problem here. We have got an increasing sequence which is pseudo-binary. It's like binary with 3 ones, because you only get 3 powers of 2. So find the largest value of the integer n such that an is less than or equal to 2020 means how many of these modified binary values are going to be less than or equal to 2020. And so if it's less than or equal to 2020, what I can do is to just write down the whole bunch of powers of 2 Now, I'm writing them backwards, but in practice, obviously, if you're calculating them, you will be writing it the other way. Now, what I notice is that 2020 is very close to the next power of 2. You can't use that, but if you use any 3 of these, it will sum to less than or equal to 2020. Take the 3 biggest ones and it sums to about 1800. So you're pretty safe. And also, because of our idea of binary, we know that any 3 of them will have a different total. Which implies that the largest value of n, which means how many numbers fall under 2020, is just going to be 11 choose 3, because any combination of 3 is going to work. And that's the end of the bunch of tips that I have for the SMO Open. It's a bit incomplete feeling, right? Well, that's the point. One of the most important things for the SMO Open is just to realize you're not going to be able to do everything in time, or even to try everything properly in time. So I would suggest pick and choose your questions by looking at everything first. Look for questions that you can do. Look for questions that have the ideas which I have discussed. And then look for questions which appear that they can be tackled using SMO Junior or SMO Senior ideas first. That's usually the best strategy, and it is definitely going to give you enough questions to get a very decent score. Alright, so that's all for me. All the best, and if you have any other questions or comments, please leave them below, and I do look forward to seeing you in the review session in a few days' time. So all the best everyone, and goodbye for now.